Hello, everybody. Thank you very much for joining us for this webinar on the Sustainable Development Scenario. Over the next hour, we're going to be presenting some of the main findings from the work which we carried out this year as part of the World Energy Outlook 2019 on the Sustainable Development Scenario. We'll be presenting for around about 30 or 35 minutes, and then there'll be time for questions and answers after that. Hopefully you all have access to the text box via the website. Do feel free to add your questions, and we will try to address as many as we can at the end of the presentation. Just by way of introduction, my name is Christoph McGlade. I'm one of the authors of the World Energy Outlook, and we will be hearing from a number of the other authors who worked on the Outlook this year. But before getting into the scenario itself, I think it's helpful to provide some context for where we see the energy world today, because I think it's fair to say that there are a number of deep disparities or discrepancies that define today's energy world. So, first of all, for example, we have the promise of modern energy for all, which is a key element of the UN's Sustainable Development Agenda. Yet, despite these promises, we still see that around 850 million people around the world don't have access to electricity, and even more, around about 2.6 billion people don't have access to clean cooking facilities. They rely upon solid biomass as a cooking fuel with negative impacts for health, and particularly impacting women and children in particular. We've also seen growing awareness, on the one hand, of the impacts of air pollution on people and cities around the world. And yet, unfortunately, the situation still seems to be getting worse. Around about 3 million people died prematurely as a result of outdoor air pollution last year, and a further 2.5 million people died prematurely because of indoor air pollution. And again, for both of these types of pollution, the greatest burden is felt in the developing world. And finally, we have the discrepancy that exists between the wealth of scientific evidence stating that the world needs to urgently curb greenhouse gas emissions in order to avoid the worst impacts of climate change, and the fact that emissions continue to reach historic highs. But while these are all, I would say, relatively negative influences and ways of viewing the world, we shouldn't forget that there are some positives. We have seen cost reductions, innovation happening, particularly in solar, wind, electricity storage, digital technologies, and others, which reduce the costs for these technologies and help us to provide a cleaner and more sustainable energy system going forwards. And one of the key themes that we're going to be discussing today is that there is a real need for policymakers to provide the right conditions for these technologies to grow at the scale and pace that's needed. I should highlight that it's a question that we're often asked regarding the World Energy Outlook, is whether we provide forecasts as to what's going to happen. The unequivocal answer to that is that we don't, but we do provide different scenarios as to what could happen in the future under different situations. We have what would happen if there are no additional changes to the current policy makeup around the world, our so-called current policy scenario. We have the scenario which changed its name this year, called the stated policy scenario, which considers both those policies that are in place around the world and the targets and ambitions that have been announced by governments and industries. This scenario is designed to look at the implications of these announcements. And again, the aim is not to predict the future in that scenario, but to hold a mirror up to policymakers to show them the consequences of decisions that they're making today. But as we highlighted, the main thing that we will be discussing in today's presentation is on the Sustainable Development Scenario. And as I'm sure as many of you are aware, the Sustainable Development Scenario contains within it 3 main pillars, all relating to the energy related parts of the Sustainable Development Goals. So first of all, we have action on climate change, bringing about emissions reductions that are in line with the Paris Agreement. We have the goal to achieve universal energy access by 2030. This includes both universal electricity access for everybody and ensuring that no one relies upon unclean cooking facilities. And finally, we have the need for a substantial improvement in air pollution and a reduction in deaths that are caused by the negative consequences of air pollution. And the aim of the Sustainable Development Scenario is to work back from these goals to look at the changes that are needed in the energy system and the benefits there would be in terms of health, environment, and energy security. So when we compare the three different scenarios that I highlighted, if we look at the current trend for emissions globally, we can see that emissions continue to rise, broadly speaking, in line with what we've seen in the past. So roughly speaking, a 1% increase every year in CO2 emissions all the way out to 2050. The announcements that governments have made in terms of their targets and ambitions do make a change to the trajectory for emissions. We see that the rate of increase is much smaller. However, we don't see a peak in emissions anytime before 2050. And so this is clearly still a far way from meeting our international climate targets, or indeed for achieving any of the other goals related to universal energy access and air pollution. So stronger action is clearly needed. And in terms of the Sustainable Development Scenario, this sets out a pathway to reduce emissions down to around about 10 billion tons of CO2 by 2050. And roughly speaking, this is on course to achieve net zero emissions by 2070, as we will get to in more detail shortly. But it's worth highlighting there's no single technology or option that is needed to get us from the stated policy scenario trajectory down to the emission levels of the Sustainable Development Scenario. Efficiency is key, renewables are key, but we also see lots of other technologies such as fuel switching, hydrogen, biomethane, carbon capture and storage. No one technology can be ruled out if we are to achieve the rapid reductions in emissions that are necessary to achieve the goals of the Paris Agreement. And I mentioned that the Sustainable Development Scenario aims to achieve, roughly speaking, net zero emissions by 2070. But a key question for the Sustainable Development Scenario is, what does it mean in terms of the long-term temperature rise, and how does this compare to other scenarios that have been produced by the scientific community? So if we look just first of all at Sustainable Development Scenario, total energy-related CO2 emissions, again we see that emissions come down to around about 10 billion tons by 2050. But what will happen in terms of the long-term temperature impact very much depends upon what happens after this point. If the Sustainable Development Scenario, if after 2050 emissions fall to net zero in 2070 and then stay precisely at zero all the way out for the remainder of the century, roughly speaking, this would lead to a 50% chance of the long-term temperature rise being 1.65 degrees above pre-industrial levels. This is roughly equivalent to a 66% chance of a 1.8 degrees temperature rise. So that's the light dashed blue line there. Achieving this temperature rise, limiting the temperature rise to that level, as we can see there, does not rely upon any level of net negative emissions occurring. However, if there were to be some level of net negative emissions after 2070, we could see a peak in the temperature, and then it start to fall back towards the 1.5 degrees level. And then, given the emission reductions in the Sustainable Development Scenario, roughly speaking, there would need to be around about 300 billion tons of CO2 absorbed from the atmosphere after 2070 if the Sustainable Development Scenario is to achieve a 50% chance of a 1.5 degrees temperature rise. So again, just to reiterate, the core aim of the Sustainable Development Scenario is to achieve net zero emissions by 2070. And then what happens in terms of the temperature rise after that depends upon whether we don't have negative emissions, in which case we will end up at a 1.65 degrees temperature rise, or if we do have some level of net negative emissions, a 1.5 degrees temperature rise. And we can compare what happens in these scenarios in Sustainable Development Scenario with some of the other scenarios that are produced by the scientific community and are assessed by the International panel on climate change. So we see here in all of the light blue thin lines are individual scenarios from that have been assessed by the IPCC, and that leads to a 50% chance of between 1.5 and 1.8 degrees by the end of the century. We can also look at what happens for the 1.5 degrees scenarios that were produced by the IPCC, and we can very much see that the Sustainable Development Scenario lies in the envelope of both of these sets of scenarios. So again, if we have no net negative emissions in the Sustainable Development Scenario, we can see that it's very much at the lower end of the well below 2 degree scenarios. And again, if there are some net negative emissions, we can see that it lies within the cloud of the 1.5 degrees scenarios. And with that, I'll hand over to my colleague to speak through some of the implications for the power sector.
Thank you, Christophe. Indeed, I will be talking about the power sector for many reasons, but as shown in previous slides, we saw that the sector plays a key role in the energy transition. Many options put the energy system compatible with climate targets. But beyond CO2 emission reductions, another crucial pillar of sustainable development is to provide, for the first time, electricity access to those who are without it today. We take for granted that electricity access is at the heart of modern life. Without it, all our digital technologies, communication, infrastructure, industry, health services, and many other consumer services will not be available. This depends on a reliable supply of electricity. And for those who lack it, access to reliable electricity could provide a pathway to economic prosperity and improve well-being, which is the goal of Sustainable Development Goal 7.1. So the IEA has been working for decades on energy access issue, and our latest country-by-country analysis shows that in 2018, the number of people without access has dropped to 860 million. This is a record, but is still a lot of people around the planet in developing economy lacking these basic energy services. Looking at the progress across the world, India has been leading. There was a hard push from the government, and in 2018 alone, almost 100 million people gained access across the country. Many other countries across Middle East, North Africa, and Asia, including Indonesia and Bangladesh, have also seen significant progress. However, in sub-Saharan Africa, the population without access remains at 600 million, which is more than half of the population. Looking forward, under current and planned policy, we are not on track to reach SDG 7.1 by 2030. And 620 million people are still without electricity access. Many developing countries in Asia, Latin America, North Africa, Middle East are well on track. But these successes mean that the problem becomes very concentrated in sub-Saharan Africa. And the rate of providing access in this region barely keeps pace with the population growth, which see 2 billion people living in the continent by 2040. Some countries achieve good progress in this region. We see Kenya, Ethiopia, Ghana, Rwanda, and Senegal reach full access before 2030. However, in most other countries of sub-Saharan Africa, the momentum behind today's policy and investment plan is not enough to meet the energy needs of Africa population in full. Our SDS scenario outlines a way to leave this constraint. And according to our latest geospatial analysis, developed in collaboration with the KTH Royal Institute of Technology, achieving full access to electricity would require a significant effort, meaning tripling the average number of people gaining access every year. Today, around 20 million people are gaining access in sub-Saharan Africa. This needs to ramp up to over 60 million people per year. What we see is that all solutions will be required to reach that target. Grid expansion and densification is the least cost option for nearly 45, mainly in urban areas or for populations that are close to planned transmission grids. But decentralized solutions are also key and would provide power for more than half of the population gaining access in Africa case. This means that, in particular for standalone systems, that solar PV will be key to bridge the gap for universal access. It provides the least cost solution for over half of the 530 million still lacking access under stated policies. And Africa, and it will be key to unlock these resources. Today, only 5 gigawatts of solar are installed, less than 1% of global installed capacity, whereas Africa benefits from 40% of solar resource. Support to unlock a larger share of this vast potential would be really critical to bring deliverable, affordable electricity to millions. But beyond Africa, the rise of solar PV is global. And even under our stated policy scenario, solar PV becomes the largest source of power capacity around 2035, overtaking wind in 2020, hydro, coal, and gas. In this scenario, wind power capacity triples to 2040, and much of this growth is led by offshore wind tapping into the vast potential. Also, hydro increased with large projects, such as the one in China, second largest in the world, but also Africa and Latin America. But much more is needed to reach our sustainable goals. In the sustainable development scenario, the deep cuts in emission required, the power sector needs to proceed faster and further with the deployment of low carbon generation. Natural gas still continue to play a role to balance renewables and to displace coal. Nuclear power also make a moderate additional contribution, but the key change is the coal-fired power generation, which rapidly lose ground. And addressing the CO2 emissions from the existing fleets will be key to bring the benefits of the sustainable development scenario. I'll come back to that later. In addition, the deployment of renewable needs to accelerate much faster. They will make the vast majority of capacity addition, over 80% of addition worldwide, and they will provide 2/3 of electricity supply by 2040, led by solar PV and wind. The pace of solar PV deployment is phenomenal. It increased from 97 gigawatts in 2017 and 2018 to nearly 210 in 2030 and over 300 gigawatts per year in 2040. This means that we will experience very high share of variable renewables, and this will require an extremely flexible power system to ensure stable and secure system. The power generation will be almost decarbonized by 2050. This is critical to meet our climate goals. To sum up, new investment needs to be as low carbon as possible, and we also need to think on how we use the existing equipment to meet our climate goals, and in particular, coal plants and gas. How this strategy can be put in place. The example of a carbon neutral Europe could provide some insights. There are ongoing discussions to achieve carbon neutrality, as discussed in the EU long-term strategy, which was published in late 2018. And many countries have endorsed or are considering to complete the phase-out of coal-fired power plants. So in the SDS, with the power sector almost completely decarbonized with this reduction of coal-fired plants, shifting the emphasis for natural gas-fired capacity to provide flexibility rather than the amount of electricity. This leads to a 90% reduction of energy-related CO2 emission in the EU below 2019 level. Nuclear power in the EU also declines, even with the significant effort to extend lifetime of the aging fleet, particularly in France, and despite some new projects. A sizable expansion of bioenergy and also refurbishment of large-scale hydro plants that are existing today will help to drive the growth of renewables. Solar PV is projected to quadruple by 2050, surpassing coal-fired generation before 2025, and onshore wind becomes the largest source of electricity in the EU in 2030. But the key success story is on offshore wind. Offshore wind will become the pillar of the changing power mix in the EU. Today, this technology accounts for just 2% of EU electricity generation, but there are some very high quality resources in the North Seas, and wind offshore alone, this potential could provide 9 times electricity demand in the EU. On the path to carbon neutrality, as described in the Sustainable Development Scenario, the EU would look to produce over 20% of electricity from offshore wind by 2040. It becomes the single largest source of electricity, ahead of onshore wind, nuclear power, and bioenergy. So coming to the last part on power and how to better manage our legacy from the past, and in particular coal plants. Up to today, coal has provided very reliable, very flexible and affordable electricity for over a century, but coal-fired power generation is today the single largest source of GHG emissions. It accounts for 25% of all energy-related GHG and 30% of CO2 emission linked to the energy sector. If they continue to operate looking forward, it means, given their long lifetime, that it would lock in a significant amount of CO2 emission. So addressing this legacy is central to meet global climate objectives. So as of today, there are about 2,000 gigawatts of coal-fired plants in operation and about 170 under construction. What are the different technologies across the world? Well, over 40% of the fleet are least efficient subcritical design, which means they emit 30% more emission per unit of electricity generation than advanced design. Second, over 40% of this fleet, over 2/3 of this fleet is in developing economy in Asia. And here, the fleet is only 12-year-old on average, meaning they have still decades to operate, with implication on the related emissions. So if we look at how this will have implication on the future, existing and under construction emissions linked to these plants are the largest CO2 today. And even without new construction, they will still remain the largest source of emission by 2050. In order to successfully achieve the energy transition, as described in our sustainable development scenarios, we need to reduce sharply the emissions from existing coal-fired plants, to cut these emissions by 60% by 2030 and going to zero by 2050. Based on specific characteristic of each power plant and each market, we have assessed for the sustainable development scenario the least cost approach to address this issue and several options are needed, including first, retrofitting them with carbon capture, and this can be the case for over 90% of coal plants, and is particularly interesting for young plants of advanced technology. It can be also repurposed to provide flexibility, meaning that the capacity will be still there, but they will reduce operation, meaning electricity produced. But in some cases, we need to consider early retirements. For example, in the last 10 years, Germany has retired some 40 gigawatts of coal plants after 35 years of operation, and China retired 35 gigawatts of small and inefficient coal plants after an average of just 20 years. Of course, this option would mean that they should be accompanied by measures to tackle the related social and employment consequences, but without taking into account the existing fleet, it will be really difficult to bend the curves of CO2 emissions. And with that, I will leave you with my colleague, Daniel, who will talk more about end-use sectors.
Thank you, Yasmin. So I'm going to talk next about transport. And to set the scene with transport, around half of CO2 emissions come from LDVs. That's mainly cars, although there are some light commercial vehicles in there, and we also include motorcycles in this category. And the other half is from heavy-duty vehicles and aviation, shipping, and other modes. So in other modes, there'd be rail, and then a few that we can't neatly package up with aviation and shipping. So that's the first part of the story. The second thing that it's essential to understand is that with transport, demand for mobility sees tremendous growth over the next 3 decades. Indeed, growth in some sectors is particularly spectacular. For example, air travel is expected to increase by around 200% out to 2050. So in the steps in the stated policy scenario out to 2050, we see modest emissions growth given the massive growth in activity. But we see, interestingly, that emissions are shifted away from cars, which used to take up a 50% share, and into the other sectors. So I'm going to try and discuss why this is. This is not just because of differences in activity growth between cars and aviation and trucks, but because stated policies supporting fuel economy have a larger coverage for cars than trucks, whilst efficiency improvements in aviation and shipping are by themselves insufficient to curb emissions growth in these sectors. So I should point out that without considerable improvements in efficiency, this 2050 steps emissions column would be massively larger than what you're seeing. So we're already going quite a long way, even under steps. Emissions reductions from LDVs is also supported by the growth in electric vehicles, but other factors are also at play. Sales of SUVs have boomed to around 40% in the last few years, and this is happening around the world, not just in a few regions. Now, SUVs are around 25% less efficient than medium-sized cars, and their growth could add, we estimate, around 2 million barrels per day to oil demand by 2040, and run counter to other efficiency improvements. So that's something to watch out for. Turning to SDS now, we see a very different story, with efficiency and electrification pushed much harder than in the STEPS scenario, but these alone are insufficient to curtail growth in oil demand from hard-to-abate modes such as heavy trucks, aviation, and shipping. We need more, and that more is coming from new technologies and low-carbon fuels, which are cornerstones for supporting this transition, with a host of additional options necessary, including hydrogen-based fuels in trucks and shipping, and biofuels in aviation. By 2050, fuel cell EVs have a 40% market share in trucks, and aviation and shipping has a 40% mix of biofuels. Also, as power generation decarbonizes, the emissions reductions offered by electrification get a boost, not just in terms of the indirect emissions of charging an EV, but also from a life cycle perspective, as emissions from battery manufacturing also fall. Turning now to the building sector, we see again two very different characteristics, this time not characterized by modes, but by different regional variations. In advanced economies, limited population growth means that total residential building floor area only increases by 30% to 2050, and coupled with strong policy targets in certain regions, this is sufficient to reduce emissions across advanced economies in the stated policies scenario. For example, the Energy Performance of Buildings Directive in the EU integrates ambitious targets for reducing the energy intensity of buildings to achieve nearly zero emission building status across the EU stock by 2050. This requires a major acceleration of renovation rates and increased stringency of building codes. Saturation of appliance ownership in many advanced economies and the impact of existing and announced efficiency policies also help bring down emissions from this sector. But the story, as you can see, is very different in developing economies, where essentially we see enormous growth in activity. Residential floor area almost doubles, supporting an increase in population of over 2 billion people by 2050. In addition, developing economies experience significant growth in average incomes as GDP per capita increases by 60%. Higher incomes in developing economies mean not only larger homes, but also increasing ownership of appliances equipment, such as air conditioners. By 2050, air conditioner ownership averages about 1.4 units per household, with certain economies such as China seeing much higher levels of ownership. This compares to around 0.5 today, so it's a massive increase. Despite efficiency improvements for appliances and the application of building energy codes in certain developing countries, the increase in activity means that emissions continue to grow at a rapid rate in the stated policies scenario. Turning now to the sustainable development scenario, bending the curve to put buildings on this SDS trajectory will require significant additional efforts in both developing and advanced economies. So you can see that direct emissions in the sustainable development scenario drop rapidly in developing economies. And this is due to a shift away from coal and gas for heating and cooking in homes primarily. But also electrification tells a very different story in the sustainable development in the stated policies scenario. So in the sustainable development scenario, electrification is an enabler of decarbonization, a massive one, and indirect emissions from electrification drop rapidly in both advanced and developing economies, whereas in the STEP scenario, the stated policy scenario, electrification in developing economies actually leads to increases in indirect emissions as power sectors in those economies are slower to decarbonize. So that's the story in the building sector. And we can move on now to look at clean cooking. Turning our attention to the second component of SDG Target 7.1, which aims to provide universal access to clean cooking by 2030, we see that progress lags behind much more for this target. As we will come back to later, universal access to clean cooking is instrumental in eliminating smoke from cooking and reduces premature deaths linked to household air pollution by around 70% compared to today. As of 2018, nearly 2.7 billion people lack access to clean cooking facilities, relying on biomass, coal, or kerosene as their primary cooking fuel. Developing Asia is home to around 65% of the global population without access, or 1.7 billion people. 5 times more people lack clean cooking access than electricity in this region. Progress, as you can see, has been mainly attained in India and China. In India, 50 million free LPG connections have been provided via a high-profile government scheme. And in China, natural gas infrastructure development is helping to reduce the use of biomass and kerosene. The challenges remain acute in sub-Saharan Africa, where only 17% of the population have access to clean cooking. Looking ahead, the new policies scenario again does not see universal access by 2030. Developing Asia still hosts the largest population without access to 2030, and in sub-Saharan Africa, the switch to clean cooking turns a corner after 2030, but until then, progress struggles to keep pace with the population growth. In SDS, the projections emphasize the increase in pace necessary for universal access to be achieved by 2030. If there is a policy lesson that can be learned from recent success stories, we see that most progress has involved targeted government support for clean cooking fuels. Making clean fuels affordable is key, as it is difficult to motivate people to give up a free fuel, which biomass typically is in rural areas. This is why achieving SDG 7.1 will play a critical role in empowering women, an ambition articulated by SDG 5. This is because women primarily are the collectors of biomass in these regions. Progress on both fronts can be achieved by considering gender when designing fiscal policies, in particular fuel subsidies. For example, India specifically targeted poorer women in its high-profile LPG cooking scheme mentioned earlier. It is also important to involve women in the energy access supply chain. This has been shown to improve community confidence in the supply chain and encourage the uptake of solutions. The most affordable means of achieving clean cooking varies by region, but overall, liquefied petroleum gas is the most cost-effective means to access clean cooking more than half of the time, with most of the others moving to improved and more energy-efficient biomass cook stoves. And with that, I will move over to my colleague, Tiffany Bass, who is going to talk about industry.
Great, thanks, Daniel. So we can see that in the stated policy scenario, the emissions from industry continue to increase throughout the scenario, whereas in the sustainable development scenario, we see that industry emissions stabilize in just the next few years and enter a steady decline thereafter. Now, emissions from industry are generally considered more difficult to abate than those from other sectors for a number of reasons. These include high temperature heat requirements and that several industrial processes involve chemical reactions that produce process emissions. And so as a result, a combination of technologies and measures will be very important for reducing industry emissions. We can see that in the SDS, energy efficiency makes up the largest share of industry emissions reductions, 37%, compared to the stated policy scenario. A large portion of this potential lies in less energy-intensive industries, where efficiency standards for industrial motors are one of the most obvious options to reduce fossil fuel consumption. Next, we see that fuel switching accounts for 28% of emissions reductions in industry. The combination of fuel switching and energy efficiency together reduce industrial oil and coal consumption by almost a third in 2050. Electricity, natural gas, and bioenergy step in as key substitutes, while hydrogen also plays a role in some sectors like the iron and steel sector. Carbon capture and storage will also be key, accounting for 21% of industry emissions reductions, and it becomes increasingly important in the later years of the scenario. Its largest development is seen in the cement sector, with also considerable deployment in iron and steel and chemicals. And so we see then that there's a considerable need to ramp up efforts on CCUS in industry including further research, development, and demonstration to bring the technology to large-scale deployment in the coming decades. And just a note for those looking for more information about CCUS, that this will be one of the key focus areas of the IEA's upcoming Energy Technology Perspectives 2020 publication, which you can keep an eye out for its release this upcoming June. And finally, there's an additional strategy that I skipped over when the bars were coming out, and that would be material efficiency, which was given a bit of special attention in this year's World Energy Outlook. It accounts for 14% of the emissions reductions in industry. And this was the first year that the WEO included a broad portfolio of material efficiency strategies in the SDS with the objective of pushing further industry emissions reductions. Now, these material efficiency strategies include various actions across value chains that result in lower demand for materials produced by industry, such as lightweighting, improving materials manufacturing yields, reducing waste in product manufacturing and construction, using products and infrastructures for longer, and direct material reuse. Special attention was also made to the impacts that actions already occurring in the SDS have on material demand. So as an example, increased uptake of electric vehicles and shifting to other modes of transport impacts the amount of steel and aluminum required by the transport sector. And these type of bottom-up linkages are now integrated into the SDS, and to see their impact on industry emissions. So together, we can see that these material efficiency strategies, as well as activity changes in the SDS, lead to real reductions in demand for key industrial materials. By 2040, overall net demand is reduced relative to the stated policy scenario by 12% for steel, 10% for cement, and 24% for aluminum, thus contributing to industry emissions reductions. Efforts from government, industry, and researchers can help realize these material efficiency savings. This may include, for example, putting a greater focus on life cycle impacts at the design stage and in climate regulations, as well as developing regulatory frameworks and fiscal incentives to support material efficiency. I'll now pass it back to Christoph.
Thanks very much. So we've heard that low carbon electricity has a huge potential to play, both in terms of reducing emissions directly and in terms of reducing emissions from end-use sectors. But there are limits to how quickly and extensively electrification can occur. And we can see here the share of electricity in total final energy consumption, which grows with electricity growing from around about 20% today to over 30% by 2040. Meanwhile, the share of liquids and gases, which today are overwhelmingly oil and natural gas, drops only marginally from about 57% to around about 54% in 2040. So attention, therefore, needs to be paid to the social and environmental impacts of producing and consuming these liquids and gases. And there are two key elements to this. First is the indirect emissions that are associated with oil and natural gas. Today, the emissions associated with the production, processing, and transport of oil and gas from where they're produced to end-use consumers results in over 5 billion tons of carbon dioxide equivalent. This is about 15% of total energy sector greenhouse gas emissions. But there are a variety of different ways to reduce these indirect emissions, and perhaps most pertinently is the need to eliminate methane leaks from oil and gas operations. This is a cost-effective way to provide drastic reductions to the emission intensity of oil and natural gas supply. But in addition, as part of the drive for deep emission reductions in the sustainable development scenario, there is a need to increase the levels of truly low carbon liquids and gases that are consumed. And one of the new elements that was considered in detail in the sustainable development scenario this year is a detailed appraisal of the potential for biomethane and the role of low carbon hydrogen in the energy mix. In the sustainable development scenario, global biomethane use rises to over 200 million tons of oil equivalent, and low carbon gases make up nearly 10% of total gas supply in 2040. They're also on a steep upward trajectory and so play an increasing role thereafter. Biofuels also play an increasing role in the sustainable development scenario, with production quadrupling from around about 2 million barrels today to almost 8 million barrels per day by 2040, such that biofuels account for around about 10% of global liquids demand in 2040. Turning from the supply side onto some of the investment trends that we see, we can see here the levels of investment that are required on average each year in the sustainable development scenario compared to the investment levels that we saw over the past 4 or 5 years. And there's two striking things in this graph. First of all, is that the total level of investment that is required across the energy sector is around about $1 trillion higher than today's levels. And we should note that only a fraction of this additional $1 trillion that's required is used to achieve universal electricity access and for the improvements in air production, the improvements in air pollution that we've been discussing. But the second big factor that we see is the shift in investment flows between the different sectors. So some investment is still required in traditional fossil fuel supply, albeit much less than what we're seeing today. More investment is needed in the power sector, primarily because low carbon electricity technologies are capital intensive, even though this is offset by the lower operating costs. But the biggest change that we can see is in end use sectors, and in particularly the huge increase that are needed in efficiency investments. Efficiency improvements this year, unfortunately, fell quite markedly from the improvements we've seen across the energy sector in the past, and we need to rapidly increase the improvements in efficiency across the energy sector if we are to achieve the emission reductions in this scenario. And I'd like to finish with just a few words on how the Sustainable Development Scenario is related to the 1.5 degrees objective that is mentioned within the Paris Agreement. I mentioned at the beginning of the talk that the Sustainable Development Scenario either can lead to a 66% chance of 1.8 degrees if there are no net negative emissions, or with a certain level of negative emissions can achieve a 1.5 degrees scenario by the end of the century. That 1.5 degrees objective relies upon negative emissions coming through at scale, and as the IEA and the World Energy Outlook has highlighted on a number of occasions, there are very good reasons to limit the reliance upon these technologies that have really yet been proven to work at scale. And that's why the Sustainable Development Scenario emphasizes the importance of early action in reducing emissions. If we were to rule out negative emissions entirely and we still wanted to achieve a 50% chance of a 1.5 degrees, this would mean that global energy sector and all other CO2 emissions would need to fall to zero by around about 2050. And eliminating those 10 billion tons that we see in 2050 in a sustainable development scenario is not a simple or trivial extension of some of the change that we've been discussing so far today. Of course, there are some technologies that are available to move towards full decarbonization, electricity generation and electric cars, if they're coupled with zero carbon electricity. But there are also a number of other hurdles that need to be considered if we are to achieve net zero emissions by 2050. Just to mention a few, there are major infrastructure constraints around the world. Broadly speaking, 2 billion houses that exist today would need to be retrofitted and become zero carbon buildings. There will also be an additional 1 billion houses built to 2050, and these would also need to be net zero emissions. There is also a huge degree of need for social acceptance and behavior changes to achieve that goal by 2050. Retrofitting 2 billion houses would, of course, rely upon broad public acceptance. May also be a need to curtail air travel, as it's uncertain whether low carbon fuels will be fully available by 2050 to meet all aviation demands. A final example is dietary shifts, where a number of 1.5 degree scenarios stipulate a shift may be needed towards less meat-intensive diets. And finally, there are also distributional impacts that need to be considered in achieving net zero emissions by 2050. Some of the largest differences between achieving net zero emissions in 2070 and in 2050 would need to occur in developing economies, where in many cases the capital that is available to bring about such a transformation is much more limited. We'd also need to consider the impact of major reductions in fossil fuel consumption and therefore prices on the major producer economies that are heavily dependent upon these revenues. So just to finish, the sorts of changes that we see in achieving net zero emissions by 2050 go well beyond the normal analysis of just the energy sector. It will be a huge task for society as a whole and would likely involve widespread behavioral changes. And it bears repeating that there's no single or simple solution that can be effected to turn emissions around. All technologies, all fuels, and all emission reduction options would need to be taken into account.
And with this, I'd like to thank, my name is Laura Cozzi, I'm the Chief Energy Modeler here. I'd like to thank very much all the authors of the Sustainable Development Scenario this year that took the time to speak with all of you today. So once again, thanks to Christoph McGlade, Daniel Crow, Yasmina Salan, and Tiffany Vaz, but there are many other colleagues in the WEO team that contributed, and many thanks to all of them for having put forward this comprehensive and detailed analysis. For those of you who are interested in knowing more, we'll certainly invite you to go to our website and find more information and data that are freely available there. For those of you who are at COP, I invite you to visit again our website. We have a list of analysts present on site this week and next week, including one colleague from the WEO team, Stephanie Bouquet, that will be also available to answer more detailed questions on our scenarios. We have a few minutes more to take a few questions that are coming in from the audience that has been following up to now. We may want to start with the one about oil and gas investments and the trajectory that you're seeing in our sustainable development scenario. So the question asks, we are hearing a lot of feedback from investors and other communities of the need of divesting from fossil fuels as soon as possible. What's your take and your analysis? What does it tell the sustainable development scenario vis-a-vis investment in fossil fuels? And I would like to ask Christoph McGlade to give us the answer.
Thanks, Laura. So as I noted, there is less investment in fossil fuels in the sustainable development scenario than we see today, and indeed less investment than occurs in the stated policy scenario. But there is still a need for some investment going into oil and gas production. And the key reason for this is that the declines that we see in current sources of production exceeds the declines in oil and gas demand in the sustainable development scenario. So to put some numbers to that, at the largest drop that we see in oil demand, for example, in the sustainable development scenario is in the 2030s, and demand drops by around about 2% every single year. If we were to completely stop investing in any new projects or to invest in existing sources of production, this would mean that oil supply would drop by around about 8% every year. If we continue to invest in existing sources of production, but we don't open up any new fields around the world, then total oil production would drop by around about 4% every year. So whether it's 8% or whether it's 4% decline, those numbers far exceed the decline that we see in demand. And as a result, some levels of investment are needed into both new fields and existing fields to make sure that we have a smooth matching between supply and demand going forwards.
Thank you very much, Christoph. We have another question actually on shipping. Again, asking to go a bit more in detail on our finding on shipping. Shipping, we hear it's a large part of emissions today. There is a bit of tension between current regulation of IMO that is requiring sulfur to be eliminated as soon as possible and a longer-term target. I'll maybe ask Daniel to give us a bit of our assessment in terms of shipping.
Thanks, Laura. So shipping today accounts for around 3% of annual CO2 emissions, but this is set to rise markedly under current policies. Shipping's quite a hard sector to figure out and quite a hard sector to model because you have long lifetime assets in which operators and owners are often motivated by sometimes conflicting economic interests. So it's quite a hard sector to get right from a policy perspective, quite a hard sector to design a policy for. Next year in 2020, we have the sulfur cap being introduced, which will drastically reduce the legitimate amount of sulfur emissions from 3.5 to 0.5% from international shipping. And shippers really have a few options in the short term to deal with this. One is that they can fit scrubbers, which remove sulfur from exhaust as it comes out of the flue. And another option is that they can use low sulfur fuels. Broadly speaking, we find uptake of both scrubbers and low sulfur fuels. There's no sort of easy, obvious winning solution, although scrubbers can't be retrofitted to much of the existing fleet. Going forward to 2050, of course, we have the 50% IMO greenhouse gas target, so it's a 50% reduction on 2008 levels. And this poses challenges for the fleet. Some shippers, notably Maersk, have committed to 50% reductions. They're sort of early movers, a bit like setting net zero targets in individual companies, individual countries. But that's going to be very, very challenging. Broadly speaking, there isn't so much a technical challenge because we know how to decarbonize shipping. It's not like aviation where there are real technical challenges to do with weight and so forth. But the challenge is more going to be about the availability of biofuels and the availability of hydrogen and other such measures. So it's a very complex nut to crack, and we'll see what happens.
Thank you very much, Daniel. We also have a question on industry in particular. We have been asked, we talk about steel and cement, not so much about petrochemicals and other parts of industry. And the second question was again about industry. You spoke about resource efficiency. You think we could decarbonize without actually utilizing material efficiency and resource efficiency. And for this, I will switch back to Tiffany on taking those questions.
Thanks for the questions. So on industry, the analysis that was shown includes essentially all of industry. So this includes key emissions intensive sectors like steel and cement, but also petrochemicals and chemicals, aluminum, pulp and paper, and other smaller, lighter industries as well. And so if I mentioned more steel and cement, this wasn't because they aren't important and aren't a focus. Of course, chemicals and paper will be important, and much of the same strategies will apply for the chemical sector. Innovation will be important to bring about new technological routes like carbon capture and storage, and perhaps also hydrogen-based routes, as well as material efficiency and energy efficiency can also play a role. And on the second part of the question related to resource efficiency, certainly this will be very important in reducing industry emissions. The advantage of this strategy is that it's an option for reducing industry emissions that we already have available today, unlike some of the other low emissions industrial processes that might require further R&D before they can be fully deployed. And so it's a lever that we can really start pursuing immediately. And if we push it really hard in the next few years, it could even help us to slow growth or decrease growth in industry emissions quite soon. And so another advantage of this strategy is that we can even be seeing financial savings from applying material efficiency in that we're using less materials or reducing waste. And so in many cases, it's really about addressing the non-financial barriers, increasing planning and coordination that can help us to realize this, and indeed it will have an important impact.
So thank you very, very much, Tiffany. We have several more questions, and I'm not sure we have enough time to answer all of those. We'll take a last one, and I invite all of you that are really interested in getting replies from us to address your question via email to us at weo@iea.org. And in the meantime, I'll ask Christoph to take on this question that is about the role of natural gas in our sustainable development scenario. What happens in particular to gas demand?
Thanks very much for the question. Broadly speaking, natural gas demand grows marginally, up by around about 10% to the late 2020s. It then peaks at a global level and then falls back to around about today's level in 2040. Underlying that global picture, though, there is a lot of different dynamics that we see, and in particular, we see a big difference between advanced economies. In advanced economies, there is a need to remove coal from the system as quickly as possible, and coal to gas switching can play a key role in helping to realize quick emissions reductions in those sectors, in those regions. However, gas then, after that period of the mid-2020s to around about 2030, gas itself starts to be phased out. And we see an increase in alternatives. I mentioned some of the low carbon gases that there are, for example, low carbon hydrogen or biomethane. They play an increasing role in making up some of the reductions that we see in natural gas demand. In developing economies, generally speaking, where they are going to be relying upon coal in this stated policy scenario, any additional gas that can be into those energy systems would be helpful in terms of long-term emission reductions.
So thank you very much, Christoph. Thank you all for having followed us today. We'll post this webinar very soon on our website for availability for all of you that may want to share this with colleagues. We remain at your disposal to answer further questions via email at COP next week, and please do visit our website for more data. Thank you very much.